Our next team is also from the University of Florida, JAMA. Justifying algae's multi-purpose applications. And their project is the evaluation and design of algal growth, harvest, and utilization for various applications in Cuban infrastructure.
Good morning, everyone. We're here presenting our paper on evaluation and design of algal growth, harvest, utilization of various applications in Cuban infrastructure. As mentioned before, our name is Team JAMA. We find that very important, feeding the population of Cuba, not necessarily directly algae, but in terms of sustaining the agriculture. As you can see in our background picture, we have a plant, specifically the Papelera Cubana. It's a paper mill along the Almendares River. This is one of many plants that either go through primary treatment or dump directly into the river. Many of these plants tend to be unstable, whether they're open or closed, whether they're being renovated or repurposed for something else, or whether they're just abandoned. But there's many of them along the Almendares River. Their treatment in wastewater is questionable at best. The existing treatment in Cuba is mostly consisting of collection through septic tanks, and also what is collected through the wastewater system is, as of 2007, was 4% treated. Mostly it was a primary treatment, very well below standards. And also to take into consideration is what are they dumping into the waterways. And through primary treatment, you don't reach at any level nutrient sequestration. And specifically, it's these nutrients that over-nutrify Cuban's waterways. As you can see in this video, over-nutrification in rivers and the oceans can lead to a lot of different impacts. This video specifically is focused on one of the most famous examples of algae. It's harmful algal blooms. And one of the most prevalent ones to humans is the disease of ciguatera. This disease is related to herbivorous fish that eat the algae that have the toxins. The toxins accumulate as fish eat other fish. And by the time the fish get to the humans, this is not a toxin that you could just cook and it'll die. So it'll accumulate enough and definitely create an impact on humans. Depending on what strain of the disease it is, it'll have neurological effects, but it could also have digestion effects as well. And they do a lot of research of this in Cuba. Recently, they discovered various algal strains that are specifically related to this, both microalgae and macroalgae, and it's a big deal. Here you can see some factors influencing the growth of harmful algal blooms. It has to do a lot with the nutrification we mentioned. You can see in the picture agricultural runoff in terms of artificial fertilizers along the coastlines used in agriculture, and consisting of nitrogen and phosphorus based fertilizers. That, along with urban runoff and industrial runoff, you could lead to these toxic algal blooms. And the other big impact of algal blooms in Cuba is eutrophication, specifically the deoxygenation of water. As you can see, there's large green swaths of algae along the coastlines in Cuba, specifically around Isla Juventud, and along the coastlines in the north. A lot of these green swaths could mostly be non-harmful algae in terms of creating toxins, but in terms of deoxygenating the water, that as the algae dies, in the next slide, as nature tries to absorb all these nutrients in the form of an algal bloom, the algae will eventually die out, and creating a surplus amount of organisms in the ocean that bacteria try to decompose. And in that process, the bacteria absorbs oxygen and deoxygenizes the water, and it will either kill off fish and sea life that can't escape it, or just create dead zones overall where fish just don't want to be there. So what do we propose for this? We're proposing a supplemental treatment using algae, nature's intended solution, but in a more controlled manner, so that it creates less of an impact on the on nature. So instead of depending on fish to consume excess algae, we'll grow the algae on land and use it as for human consumption in terms of using it as a product. As you can see, Cuba is a very good fit for algae in terms of solar radiation. This map shows kilowatt hours per meter square per day along the whole island of Cuba. It hits a sweet spot in the sense that it's not too much sunlight that would be unfavorable for algae in terms of high temperatures. But it's also just enough that it can lead to algae growth throughout the whole year. Cuba has experience with algae. They've done plenty of research. Algae is a technology that's not new at all. It's been going on for decades. And what Cuba has tried is concrete raceway ponds. It's a traditional form of growing algae at low cost. Concrete tends to be very permanent, however, and wherever you put it, you pretty much have to leave it there. They also do research scale algae growth. In this case, they were growing spirulina on Habana rooftops, along with a lot of other solar research. Specifically, this is a Cuba Solar research team. And they have inclined canals growing chlorella. The model we proposed is using a raceway pond coupled with the industries that cause the most pollution. Specifically, paper mills. There's been plenty of research done on how effective are algae in decontaminating paper mill wastewater. And they're good at removing color, dyes, and a lot of things that you wouldn't be able to do with a traditional wastewater system unless you had very expensive tertiary treatment in terms of removing the nutrients and dyes. As you can see in the model, it's made out of wood. We took that into consideration for sustainability and also for portability. If they ever need to take this down because the plant shut down, or they need to move it somewhere else, or they need to expand it, this is a lot more flexible than concrete would be. We also elevated the electronics to protect them from potential flooding. And we based the whole system on a 1.5 horsepower motor, some car batteries, and solar panels. There's also the other option of closed photobioreactors. These are specialized in absorbing flue gas from plants, which is another source of pollution. But in another way, it's also a source of nutrients. And CO2 specifically helps prosper algae. And these closed photobioreactors would be the perfect example of utilizing the CO2 and the flue gas to its full potential. The design we're proposing is also using wood frame structure. And we purposely wanted to take into consideration adjusting angles for different scenarios in Cuba. If there's not as much sun available, if it's in a crowded urban area, you can change the angle, take into consideration the sunlight that you do have, and focus for optimizing sunlight. And also for portability in terms of if you need to put it away to protect the structure, you could harvest algae, fold it, and tuck it away somewhere. Now, Arturo on our system.
Hi, my name is Arturo Cancino. I'm a computer engineering student, a bit of an oddball here. So how does the entire system come together? Our main source of wastewater will come from the paper mill. This wastewater will be directed onto our open pond system via water pumps and valves. In the open pond system, the algae will take advantage of the nutrients contained within the wastewater coming from the mill and the light from the sun in order to grow. A percentage of the water that's inside the open pond system will be redirected onto the photobioreactor. The photobioreactor will take advantage of the carbon dioxide contained inside the flue gas that is coming out of the smokestacks from the paper mill. The algae contained within the photobioreactor will take advantage of the sun, as well as, like I mentioned, the carbon dioxide in order to expand and grow. We will be gathering algae from both systems, the photobioreactor and the open pond systems, and feeding the algae and using the algae as animal feed. Now, what you see here is control. What I'm trying to display in this slide is a way to implement control onto our system. We have decided to implement electronic components onto the photobioreactor and the open pond system in order to gather additional data that would help us control and modify the system to optimize algae production. As you can see in our model here, we have implemented an Arduino board that takes readings, which is what you see now, from the water temperature inside the open pond system and reports it onto a computer. This is an example that we have actually implemented in our model, and there's additional things that we can do to apply further control into this type of system. A few examples are pH level readings, as well as carbon dioxide and hydrogen level readings that one can monitor and adjust to maximize algae production. Now on to the financials. It's important to note that a system such as this has not been, it's not a popular choice as a solution, has not been implemented before. Therefore, it has caused a few difficulties when it comes to coming up with long-term financial projections. What you see here is a basic layout of all our estimated costs to create a single system that includes both the photobioreactor as well as the open pond system. We estimate a total of $4,780 for the photobioreactor and an estimated $2,256 for an open pond system. This is a total of $7,038 for a single system implemented in just one factory. This is not the cost to fix the entire infrastructure. Now on to some facts. In 2012, Cuba purchased about 49% of their total meat source from external sources from other countries. Yeah. About 42% of Cuba's expenses from food sources are dedicated to animal feed and swine food. As you can see in this graph, the highest amount of money spent on soybean is about $65 million from the United States. This was from 2000 to 2012, as you guys can see in this graph. The reason I bring this up is because soybean is a popular protein used as cow feed and as swine feed. As you can see, chlorella and spirulina, which are both types of algae, are both competitive and can be compared to, if not, are not more effective than popular protein choices such as soybeans and eggs.
My name is David Cabrera. I'm a fifth-year mechanical engineer. And let's talk about some human and environmental impacts. So Cuban citizens and tourists both, they deal a lot with waterways in Cuba. So when you mistreat waterway systems and you let water get polluted, this can affect humans because they're very easily contaminated with, as previously stated, like brain diseases and stomach diseases. This is also bad for the environment because of eutrophication. We could actually leave Cuba's waterways without oxygen, therefore without animals. I mean, can't contain life without oxygen. So one of the big problems with Cuba is with this current infrastructure in wastewater management. In order to redo or to fix Cuba's current infrastructure, it would take something in the magnitude of billions of dollars to replace what's currently there. Not only would it cost a lot, but it would also affect many of the existing infrastructure. As this picture shows, in order to remove piping, you're going to have to destroy streets. And the way Cuba works, the streets will probably have to be closed, and they'll probably have to be closed for a long period of time since the materials aren't readily available and transportation isn't the best. So one of the big things that we cared about when coming up with the design was risk mitigations. We wanted to make sure that our system was safe for public and for environmental reasons. So the biggest concern we had was high winds. High winds can create permanent structural damage, and it could also release our strands of algae into the environment. So how do we prevent this from happening? We prevent this by making our system as very easy to put together and to take apart, as shown by our sample photoreactor, we can just bend it and store it in case of a storm or hurricane. So what happens if, for some reason, the water that's being used to feed the algae it's got too many contaminants? Well, we could use that batch of algae as compost for aguaponicos. Aguaponicos are community gardens which are used to grow food in Cuba. And if the algae is not good enough for aguaponicos as compost, we can use it as biogas. So Cuba's been using biogas as an alternative energy source for quite a while. Lately, they've been spending a lot of money and research into it as a form of energy. So whatever we can't use as animal feed and whatever we can't use as compost, we can use as biogas. There's a lot of applications when it comes to algae. Currently, Cuba is growing specific strands of Chloridea to use as medical components, and there's more applications. For example, biogas, biofuel. Cuba's done a lot of extensive research on biofuel, and as shown in this graph, microalgae is far above in oil yield in liters per hectare than normal traditional methods. Any questions?